Welcome back to the Renaissance. It's Venus. In today's video, we are going to talk about the history of the atom and the theories and models behind it. So, let's draw a mind map with me of atom and the theory and model behind it. So first off, we have Democritus, who is a pre-Socratic philosopher. He was around in 400 BCE, and he is often referred to as the father of atomism. So Democritus proposed that all matter is composed of indivisible, indestructible particles called atoms. So atoms are the fundamental units that everything in the universe is made of. Back in the days, they couldn't do experiments to prove the existence of atoms. Everything was speculative, but Democritus' ideas was revived in around 17th to 19th centuries by scientists like John Dalton, who we are going to talk about. So Dalton was probably the first man to develop the scientific atomic theory in the early 19th century. Building on the ideas of Democritus, he introduced a more structured and evidence-based model of the atom. However, there are flaws to his theory that atoms are indivisible. As we know, there are subatomic particles like electrons, protons, and neutrons. The second thing is he argued that atoms of the same elements are identical in mass and properties, which we know isn't true because isotopes exist. And also, this simple model does not provide explanation for chemical bondings. However, Dalton still contributed a lot in terms of how he categorized elements by atomic weights. The idea of the atom being the smallest indivisible unit is rejected by J.J. Thompson when he discovered corpuscles, which are later named as electrons by Stoney. The discovery of electron is the first discovery of a subatomic particle, proving that atoms were not indivisible. This led him to develop the Plum pudding model, which the atom is thought to be a positively charged pudding, like a diffuse cloud of positive charge, and electrons are embedded in it like palms, like the bits in a cookie. As we know, that's not entirely true, and here comes Ernest Rutherford with his golden foil experiment in 1911, which disproved the plum pudding model, showing that atoms have a dense nucleus, where the positive charge is concentrated at. So this later paved the way to the discovery of protons and neutrons, but Rutherford still can't explain electron stability because classical physics predict that orbiting electrons should lose energy and collapse into the nucleus. And also he did not provide explanation for electron arrangement, which will be addressed in later by quantum mechanics model by Bohr and Schrödinger. So Bohr says that electrons orbit the nucleus in fixed discrete energy levels we call shell, and nothing can exist between these levels. Unlike Rutherford's model, Bohr proposed that electrons in these orbitals do not lose energy, and hence solving the collapse problem. And electrons can jump to higher orbits by absorbing a photon with certain frequency. And when it falls back to the initial state, initial level, they emit energy as light, which explains some spectra like the hydrogen, the atomic spectra, and it matches the experimental data for hydrogen. However, the model really just kind of worked for hydrogen, and it failed for multi-electron atoms. And also it ignored the electron wave particle duality, which is a instrumental concept in quantum mechanics. So his Bohr idea is oversimplified, and we need to count on Schrödinger's quantum mechanics and chemistry model to supplement and explain for the fact that electron paths are probability clouds. So the heart of Schrödinger's quantum mechanic model is wave function. Electrons are described as standing waves around the nucleus, not fixed orbits. So the Schrödinger equation allows you to calculate the probability of finding an electron in a region, like say the orbital. So it kind of unified wave particle duality of the electron and explain complex atoms, unlike Bohr's hydrogen-only model. So, and Schrödinger model can predict chemical bonding using molecular shapes like VSEPR and hybridization. Schrödinger equation is still used very frequently by computational chemists to predict bonding and orbitals in chemical molecules. The backbone of the method is still the quantum mechanic model of Schrödinger's, but approximation and assumption and optimization on relativistic effects on electron-electron repulsion and many-body problem are being used to optimize the computation. Alright, I hope you enjoyed this video, and here is the mind map. It's a not so complete representation of the development of the atomic model, but I hope you enjoy it, and subscribe to listen to me talk about chemistry another time. Also, if you enjoy it, don't forget to give this video a thumbs up and comment about the content you would like me to talk about in the comment section down below. Take care and see you next time.